started?
Yes. So it's a pleasure to have Vincent Bouchard with us for today's talk. He will be talking about some new topological recursion formula for n is equal to 2 supersymmetric theories using his recent work on the mathematical side. So welcome everybody, and let's get started. So over to you, Vincent.
All right, so hello everyone. Thank you for the invitation. It's probably the first time I give a talk on 2 days at the same time, so it's kind of interesting. So we're both the 14 and the 15. So yeah, I'll talk about Whittaker vectors for W algebras from area structures of topological recursion. So this is work with Jeta, Nitin Chidambaram, who's in Max Planck, and Thomas Kreutzig, one of my colleagues at the University of Alberta. So this is a paper that just came out a few days ago. So you can look at the archive if you want more detail, because I won't be able to explain every single thing in the paper in this talk. But I'll try to be fairly general. So please, as always, do not hesitate to ask questions. I can see the chat, so you can use the chat, or you can turn your mic on, interrupt me, and just ask your fantastic questions. So we'll get started. So the setup here is, as was mentioned, is n equals 2 four-dimensional supersymmetric gauge theories, something that has been studied a lot in the last little while. So we'll talk about AN, BN, CN, DN, so all ABCD stuff. And the main object of interest in these theories is the partition function, or what's called Nekrasoff's instanton partition function. So I won't define these things here because otherwise that would take way too much time and I wouldn't be able to go to what I want to talk about. But the key that I want to mention here is that this partition function, as is well known now, can be obtained as the norm square of a vector. And I'll explain what these things are in this talk. But this is something that is called the Gayotto vector now. And that vector is going to be the main object of this talk. So we're interested in the partition function, but we will not construct the partition function directly in this talk. What we'll do is construct the Gayotto vector, and then the norm square gives you the partition function. So in some way, this is different from other approaches that have existed using cyclic Witten curves and so on, where the partition function was constructed directly. Here we'll construct the Gayotto vector.
Is there some logic behind the fact that it can be expressed this way?
That it can be what? Sorry?
That the partition function can be expressed as the norm of some vector.
Well, sure, yeah, I don't know. I mean, this is an old, well, I don't know if it's old. I don't know all the details of
no, I'm just asking for an intuition. Is there any intuition, or it's much? If it's complicated, I don't know. It's okay.
I don't know how intuitive it is. I don't know.
I think maybe there's an intuition
I can say.
That this is counting instantons on S4, and somehow the Gayotto vector, I want to think of it as the instant partition function on the hemisphere. And you glue 2 hemispheres to get the S4.
So it's like topological anti-topological fusion.
That's how I think about it.
Okay, okay.
Yes.
Thank you.
Okay, thank you. All right, so this Gayotto vector is going to be the main object of study in this talk. And of course, you can reconstruct the partition function from it. So our goal will be to construct, in all these cases, A, B, C, D, this Gayotto vector using what we call topological recursion. So for those not familiar with this, I'll explain what this is. More specifically, what we'll use is the reformulation of topological recursion by Kontsevich and Sobelman, which has become known as area structures. So this is the main goal of this talk, is to basically construct this Gayotto vector very explicitly in all these cases, in a very, very explicit, so a recursive way, so we can construct everything very explicitly using topological recursion. All right, so that's pretty cool. So that's the goal, compute the Gayotto vector using topological recursion methods. So why should you care? Before we get into the details of it, maybe you might wonder why you should even listen to this talk or read the paper. So there's a number of reasons. For those familiar with topological recursion, so this is an area that has been extensively studied in the last 15 years, maybe. It dates back to Chekhov and Arendt. Topological recursion was studied a lot. Basically, there's a lot of structural properties, lots of things that are known just from the structure itself. So all these things that exist can be applied to the Gayotto vector if we can realize the Gayotto vector using topological recursion. So that might give rise to a lot of new results in supersymmetric gauge theory. I don't know, maybe, but that's a possibility. So connecting two different areas is always a very fruitful, or can be a very fruitful thing to do. One thing that's interesting is that we're working on a general omega background in a sense where we're considering general arbitrary epsilon1 and epsilon2. So that's kind of also interesting. So a lot of the work has been usually just as an expansion in H bar, but not in the full generality that we're doing things here. One thing that's interesting as well, as I mentioned before, is we're constructing the Gayotto vector directly instead of the partition function. So that's new in some way compared to the previous approaches to this problem. And as I'll explain, the Gayotto vector will be related to Whittaker vectors. It will be given by a Whittaker vector in VOAs and vertex operator algebras. So connecting area structures with these Whittaker vectors may also help understand Whittaker vectors in VOAs, which is something that is still fairly, I would say, I mean, some things are known, but there's still a lot of unknowns about Whittaker vectors in VOAs. So that's a different direction, but there's a lot of different things that this connection between area structures and Gayotto vectors may give rise to. All right, so this is just to motivate why you might care about what I'm going to talk about, but now let me get into some of the details. Well, before I get into the details, let me just mention how we're going to construct the Gayotto vector. Basically, there's a key theorem that we will use. This is the starting point of our work. So this is a theorem that is due to Braverman, Finkelberg, and Nakajima, which is the following, which is that the Gayotto vector is in fact a Whittaker vector. And I'll explain again what this is in a few slides. For a particular vertex algebra, which is a W algebra, at a certain level. So in other words, it's a Whittaker vector for a WG module. So G here is a simply laced Lie algebra. So this is only the A, the E case, but for the B and C case, as I'll mention later, we can also construct the Gayotto state, the Gayotto vector as a Whittaker vector, but it's slightly different. So it's still an ADE case in some way. It's just that we have to introduce a twist. But this is the key result, that the Gayotto vector should be a Whittaker vector for W algebras. So what we're going to do is now construct these Whittaker vectors using area structures. At least that's the goal of this work.
Can I ask a very naive question again? It's probably on the physical side.
Yeah.
So in all this, does this 4D, 2D correspondence play some role? Because when you're talking of this vertex algebras, this looks like you're doing some 2D thing, computation and.
Yeah, so first I should say that all physics questions will be answered in a very bad way because I'm new to this side of the physics, so I really don't know much about this. But yeah, I mean there's this appearance of these W modules, of course, coming from a 2D. I actually don't know. Maybe Gaetan, you have a better answer. You know the physics much more than I do.
I think it's so. Actually, this theorem is a mathematical incarnation of the Aldai-Gayotto-Tachikawa conjecture, and indeed, I think they use this sort of 4D, 2D correspondence to propose something like this, and then it was proved. So first by Vasro and Schiffman for the A type. And then for this general simply laced type by BFN.
Okay, I was thinking indeed there should be something to do with AGT. Thanks. Yeah.
No, exactly. That's exactly where it's coming from. Is the relation between CFT and the AGT correspondence here. That's what the statement comes from. Yeah. Sorry, I should have said that. No, sorry, I thought that. Okay, I should have mentioned that. Yeah. Thanks. Okay, so this is the starting point. So now what am I going to talk about? Well, first I need to define these things. So my rough outline is that first I'll define what a Whittaker vector is from the point of view of VOAs, vertex algebras. Then I'll define what an area structure is, because I presume most people don't know as outside of the community of topological recursion practitioner, if I can say. And then I'll explain how these two things are connected. So how we can use area structures to construct Whittaker vectors and what kind of things that tells us about these Gayotto vectors. All right. Okay, so let me just start by defining Whittaker vectors. So first I have to define W algebras, which is where we're gonna, where these Whittaker vectors will live for this talk. So I'm gonna focus mostly on GLR here just to make things concrete. So in fact, I mean, this is SLR, but we usually extend to GLR because it makes things nicer in the construction, but really you could do it both ways. But what we're going to do here applies to any simply laced Lie algebra here. Okay, so first let me just define what a vertex algebra or VOA is. I'm not going to define it, but just to give you the general objects that you're working with when you talk about VOAs. So you first have, so as you all know probably, vertex operator algebras are some sort of axiomatic formulation, mathematical formulation of chiral conformal field theories. So it's just one mathematical way of thinking about CFTs. So roughly speaking, so everything you know about CFTs is kind of reproduced in the mathematical language of VOA. So V is your space of states or vectors that live in V. You have a state field correspondence, Y, which is a map from your field to endomorphisms on your space of states. And these are formal series in Z. So for example, if you take a vector V in capital V, then the corresponding field is going to be an expansion. So the way I'm going to define the, sorry, that should be V, the terms here, which we call the modes, is by shifting here by delta. So let me define what these things are. So this is what we call a state or a vector. That the Y of this is what we call the field. So often I'm going to use the notation V of Z as being the field corresponding to the vector V. These are the modes here of your field. And here, usually in VOAs, it's often defined, the shift here is 1, but there's two conventions, either 1 or delta. Delta here is the conformal weight. So this makes sense if your state is an eigenstate of your Hamiltonian. So you now have some Hamiltonian in your that acts on your vector, and this is an eigenvector with eigenvalue delta. So the way to think about this is if there is a conformal state, so if basically there's a Virasol field in your theory, then this would be usually the zero mode of your Virasol field. So it is really the conformal weight as you think about it in CFTs. All right, so this is just to say that I'm shifting by conformal weight, which is how we do things in this work, but there's two conventions. You could shift by 1 or conformal weight. All right, so the key point here is that to a state, you have a corresponding field, and its expansion gives you modes. So that's what you should know. And then, to define VOA, there's a bunch of axioms that these things should satisfy, but I'm not going to write this down. They're there to reproduce the structure of CFTs. All right, and the key point about WGLR, so sometimes we have a K here, sometimes I might drop it. This means the level. I'm not going to talk or define what this is in this talk. But the key point of these, this is an example of a VOA vertex algebra, and it's strongly generated by, it's fairly simple, and it's strongly generated by a bunch of fields. So strongly, well, let me write it down first, and then I'll say what it is in words. And these have conformal weights 1 to R. So you have R fields, each of conformal weight 1 to R. Strongly generated means that you can construct all the states in your space of states by acting on the vacuum with the negative modes of these fields. But it's not negative, it's negative if you shift by 1. If you shift by conformal weight, it would be conformal weight -1. But anyway, if you shift by 1 for that particular definition, then all the space of states, or rather the space of states is spanned by all the products of negative modes acting on the vacuum. So that's what it means to be strongly generated. And that will be important for us. So everything we do applies only to vertex algebras that are strongly generated. We don't really know how to do it if it's not strongly generated. Okay, so that's cool. That's all I want to say about a definition of W algebras. What you should remember is that you have R fields here, and they all have conformal weights 1 to R, and they strongly generate the algebra. So everything is constructed out of those. Now, what is a Whittaker vector? So first, you have to define a Verma module. So a Verma module for your algebra is probably, you might know what this is already, but very roughly speaking, what it is basically you start with the highest weight vector. So you take what is the highest weight vector. So you have a vector in your space of states, which we usually denote like this. So this is inside your space of states. And it's such that this vector is killed by all the positive modes. So if you act with any positive mode, so this is for I 1 to R, so you take any of the modes of the strong generators, you act on that state with the positive modes and you get 0. And with the 0 modes, you just get basically some value lambda. So these are eigenstates. And lambda i's are just some complex numbers here. And that gives the highest weight. So that's why it's called highest weight state. And the Verma module is now obtained by acting on this highest weight states by all products of negative modes. Now negative meaning negative with respect to that definition here. So you act with negative modes on those, all kinds of products of negative modes of the strong generators on lambda, and that generates the Verma module for your vertex algebra. Okay. It's a crash course on vertex algebra from someone who is far from being an expert on vertex algebra. Now, what is a Whittaker vector? Well, a Whittaker vector is a very particular vector that is an Verma module. So it's going to be a vector, omega, inside this Verma module associated to the highest weight states, such that it's almost like this, but not quite. So it's killed by all the positive modes except one. So this is going to be the definition we take in this paper. This could be extended, it could be generalized, but this is the definition we take because that's what is relevant for the Gayotto vectors. So more precisely, what I'm saying is that this is equal to 0, except for one mode, which is when I is equal to R. So this is the modes of the generator with the highest conformal weight here. So I equals to R, this has conformal weight R, which was the highest one in the list of generators. And it's the one mode. So K is equal to 1. So basically, this state is killed by everything in the positive, all the positive modes except 1. And it's an eigenstate of that particular operator WR1. So lambda here is just a parameter. So it's just a complex number. So this will play the role of the energy. In fact, it's the energy, plays the role of the energy scale in the supersymmetric gauge theory. Okay, so again, this is for I equals 1 to R and K greater than 0. Okay, so this was the definition of Whittaker vector. And now the statement of Braverman, Finkelberg, Nakajima is that the Gayotto vector is actually such a Whittaker vector. All right, so more precisely, the statement is that the Gayotto vector, this is a theorem, is that the Gayotto vector, so they do it for simply laced Lie groups, so AD. So the Gayotto vector here is a Whittaker vector for a particular WG module, so G is the corresponding Lie algebra. So in the case of I'm focusing on in this talk is GLR here. And then there's a particular level. So each of these W algebra comes with a level. So here we're looking at a particular level, which is in fact given in terms of epsilon1 and epsilon2, where epsilon1 and epsilon2 are the standard parameters in your supersymmetric gauge theory. And that's basically the theorem. So what we're trying to construct is Whittaker vectors for these Verma modules for W algebras at this particular level.
Given a module, is it unique, the Whittaker vector?
So yeah, that's a very good question. So in fact, yes, that's something we prove, in fact. But it also follows from the theory of area structures. But yes, given a Verma module, so a highest weight state on a Verma module, of course, I mean, there's the lambda here, there's a dependence on this parameter, but yeah, then it is uniquely defined. Right, so in fact, a remark which is related to that is that in our paper, we also prove a few results just in terms of vertex algebra themselves, so without relating to area structure. And one of them is that we prove existence and in fact uniqueness of this Whittaker vector for whenever for all Verma modules m lambda that are simple. So I'm not going to define what this means, but basically an example of this is all principal W algebras, which is exactly the W algebras we're looking at. So we kind of prove the existence of that, the Whittaker vectors, just from the vertex algebra themselves. But I don't want to talk about this in this talk because I want to focus on the relation with area structures.
Just one question: is kappa can be arbitrary in this way of reformulation?
Yeah. So that's actually one of the cool thing with what we're doing. So I mean, epsilon1 and epsilon2 are parameters in your gauge theory. So in principle, kappa would be arbitrary. I mean, there's going to be a parameter h bar that enters in the construction, which is this, and then you have kappa, which is minus epsilon1 or epsilon2 over epsilon1. So in general, you can have arbitrary h bar and arbitrary kappa. So kappa is the dual, the level. So a lot of the work has been done at self-dual level, where you set kappa equals to 1. Sorry, I'm slightly confused. Right, so epsilon1 equals minus epsilon2, exactly. So you set kappa equals to 1. That would be the self-dual level. So things are much simpler at the self-dual level, but and we do it for arbitrary levels. So we do it for arbitrary epsilon1 and epsilon2. I'll comment on that in a few slides.
Thanks.
Okay, so this basically was my introduction to Whittaker vectors. So what you should remember out of this is that Gayotto vectors is a Whittaker vector. So you're interested in Whittaker vectors if you're interested in gauge theories. And these Whittaker vectors are basically states in your Verma modules that are killed by all positive modes except one. That's what you should remember. So that's what we're trying to construct. Okay, so now I need to introduce the other kind of theory that we will connect with Whittaker vectors, which is the theory of area structures. So this construction is due to Kontsevich-Sabelman in a paper of 2017. It was generalized by a paper of myself with Gaetan, Nitin, Thomas, and Dmitry Nashenko, 2018. And also there's been quite a few other papers, ABCD of Topological Recursion by Gaetan, Nicolas, Jorgen, and Chekhov, and also a recent paper by Gaetan with Rainier and I forget the name of the third author. But there's been a few papers that keep on generalizing. So what I'll call area structure here is now the most general kind of construction, which probably if we were to, Rainier, Kramer, and Schuller. Yeah, thank you, Gaetan. If we were to use all the names that have been added in the generalization, this would be called a higher quantum cross-cut, probably super area structure or something like that. Whatever, it's basically just an area structure. So I'm just simplifying the name here. So let me define what this is. So it starts with a complex space, so a C vector space. The construction of area structure, I should say, is very basic. In the end, it's very simple, but it does contain a lot of pretty nice structure, and it connects to a lot of different areas, which is the power of the construction. All right, so V is a vector space. So we're going to talk about two different cases. Either it's finite dimensional. So in this case, I'll call D the dimension, and then I'll define an index set, which will be just 1 to D. But we also look at the case where V is infinite dimensional, countably infinite. In fact, all the cases we'll look at is in this case here. So in this case, the index set will be just positive real numbers, positive integers. Sorry. Okay, and then we have a vector space, so we can define linear coordinates on that vector space, or if you want a basis for the dual vector space. So these are going to be your coordinates on that vector space. And then I'm going to introduce two objects. So the algebra of formal series and these coordinates with also series in a parameter that I'll call h bar. In fact, we're working with square root of h bar for some reason. We could redefine this as being h bar square, but that's the traditional way of doing it that comes from quantum mechanics. So I'll say a few more words about this, but basically this is just the algebra of formal series in the coordinates x and h bar. And then I'll define the algebra of differential operators in these coordinates. So again, I have all my coordinates, and then derivatives, which will all come with the power of h bar. And again, these can be series and h bar, square root of h bar. So these will be the main kind of places where things will live. And then I need to define a grading here on this algebra of differential operators in MH. So my grading is going to be such that I call the degree of a coordinate and the degree of a derivative, or h bar del, and also the degree of the square root of h bar. All of those have degree 1. So that defines a grading on these algebra, which will become very important for the definition of area structure. To which I now turn to. So what is an area structure? So it is a very simple object. So an area structure is a collection of differential operators. So I have differential operators I'll call HI. These live in this algebra, completed algebra of differential operators. So here I runs from either 1 to d or all positive integer, depending on the cases you're working with. And then it has to satisfy two particular conditions. First condition is what we call the degree condition. So what that means is that these differential operators have a very special form. So they start with a term which is just a derivative plus something else. And that thing here is anything you'd like in this algebra, but with terms of degree greater or equal to 2. So in other words, what this is specifying is that the operators have no degree 0 term, and that the degree 1 term is of that form. And higher degree can be anything with respect to this grading here. And the second condition is what we call the subalgebra condition. So this is a condition on the differential operators, which is that if you take the left ideal generated, so I call S here the set of differential operators HI, with I running from 1 to d or positive integers. So if you take the left ideal generated by this set, and you commute any two elements of this left ideal, then this is inside the left ideal again, but multiplied by h bar. So what that means is that the degree decreases by 2, right? So you take something in the left ideal, you commute with something in the left ideal, you get something in the left ideal again, but with degree 2 less than the sum of the degree, or rather, there's an h bar here that comes out here. Right, this is a graded algebra. So the commutator here preserves degree. So that means the right-hand side has, or the element of the left ideal has degree 2 less than the sum of the degrees of the elements on the left. So another way of stating the same condition here is that if you take any two, maybe that'll be more explicit, take any two of these differential operators and commute them, you get h bar times a combination of these differential operators, just like you would get for a Lie algebra, but it's not a Lie algebra because these f, I, j, k are not necessarily constants. They're differential operators themselves. Right, so it's not a Lie algebra. That's why it's basically a condition on the left ideal. So the statement here is that the left ideal is a Lie subalgebra. That's another way of stating the same condition here. Okay, so this is the definition of area structure. So it looks complicated, but it really is not. It's just a bunch of differential operators that have a special form. So the degree 0 and 1 is specified, and that satisfy this condition here. So if these were quadratic, so if pi was just degree 2, the condition here would be that it's a V algebra, so the f's would be constants here. But for the higher, for the general case where you can have things of higher degree, then this becomes a more complicated condition, but it's the same, in spirit, it's the same type of condition. All right, so why should you care about these things? Well, there's a theorem due to conservative Subelman, which is that if you look at the differential constraints, so these are differential operators, so you can try to find solutions of these these partial differential equations. And it turns out that there always exists a solution, and it's unique if you specify the form. So it has a unique solution of the form of an exponential of f, where f is 1 over h bar times a series in the variables x and h bar to the 1/2. Right? Remember, M was basically the space of formal series in the variables x and h bar to the 1/2. So the free energy here, F is called the free energy, Z is called the partition function, is given in this form, and then there always exists a unique solution. So it's a very powerful statement. So that's why, in fact, the conditions here are very important. It's important. The degree condition is very important here for uniqueness of the solution, and the subalgebra condition is necessary for existence of the solution. So both of those here guarantee existence and uniqueness. And you can be more explicit. I mean, the statement that f is in 1 over h bar times this ring here is the statement that you can write a general expansion of this form. So this is the most general form. So it means that it has an expansion. It's a formal series in the variable x, formal series in h bar, but starting with 1 over h bar. And g here is a half integer, and is any positive integer. So the variables here, you have at least one of them. And 2g minus 2 plus n greater than 0 is required, so that all terms here have positive degree. Here I should have said that. So with f here, which has positive degree, according to the grading I introduced. Okay, so that's basically all there is to say about the theory of array structures, but why is that interesting? Why have people studied that? Well, there's a number of reasons. One of them is that you can show directly that these coefficients, these FGNs here are just coefficients, they're just numbers. These actually satisfy a recursion, right? This is just a standard thing you do when you do differential equations, right? You have a bunch of differential operators acting on this. You can extract from these differential equations a recursion for the coefficients. And here you can show that these FGNs are uniquely constructed by a recursion, where the recursion is over this 2g minus 2 plus n, which is the degree of these terms according to the grading that I introduced. Okay, so that's first a powerful statement, and you can write down the recursion very explicitly. And in fact, this was the original motivation of Kontsevich and Subelman. There's something that is called the Chekhov-Enal-Arantin topological recursion, which was formulated in a very different language. You start with a spectral curve, you construct some differential forms on that spectral curve, and so on. But it turns out that this is just a special case of array structure. So out of this CEO topological recursion, you can extract the FGNs, and then these are basically forming the free energy of an array structure. So there really is a dictionary between array structures and the previous formulation of Chekhov-Enal-Arantin topological recursion, which was the initial motivation of Kontsevich-Subelman to make sense of the CEO topological recursion. Now, if you don't know what this is, then you probably don't know what I'm saying here. But if you do, that was the origin of this construction of array structures. And the main reason why people are interested in these is that these are numbers, but very often they encode interesting enumerative invariants. So these would be encoding, for example, Gromov invariants of toric ideal threefolds, or depending on the array structure you choose, or they could encode Hurwitz numbers, all kinds of Hurwitz numbers, simple, double, spin Hurwitz numbers, all that kind of stuff. Basically, there are a lot of I don't know if I should say most, but a lot of problems related to moduli space of curves, where you're looking at some enumerative invariants for the moduli space of curves. You can reformulate in a generating series like this, and then it turns out that this is a solution of differential constraints that take the form of an array structure. So from that, this is also the reason why these things are interesting, is because these FGNs have often very interesting interpretation. Okay, but how is that connected? What does it have to do with vertex operator algebras and W algebras? So let me first try to summarize how you can relate the two, and then I'll be more concrete. So remember, we considered the W algebras of GLR, and then I said there's basically is strongly generated by these fields, Wiz, where I runs from 1 to R, which have conformal weight 1 to R, which is why there's this shift here. All right, so the construction is the following. So if you can find a representation for the positive modes, so there's the modes here, right? If you can represent these modes, these are operators acting on a space of states. So if you can, in other words, construct a module, so you replace your space of states by the space of formal series in variables x and h bar, and you want to construct a representations for these modes as differential operators in this algebra that I introduced, d of h bar. If you can do that, if you can construct a representation as differential operators here, that satisfies the two constraints, so the degree and the subalgebra conditions, that gives you an example of an array structure, right? Because you have now this would be a case where the vector space is infinite dimensional, countably infinite. You have an infinite set of differential operators, and if they satisfy these conditions, then you have an array structure. So that's good. So you're now back in the theory of array structures, and you can use all the results that have been proven there. And in particular, you can use Kontsevich-Subelman's theorem, which says that, well, if you have such a differential operator representations, then there always exists a unique solution to these constraints, which we call the partition function. But if you remember from a few slides ago, well, this is something that we know very well in VOAs. This is nothing else than the highest weight, than an example of a highest weight vector. Right? It is killed by all positive modes. So what we've done here is that we've identified a partition function of the array structure with the highest weight vector of the W algebra. Isn't that cool? Boom. Okay. Should be pretty awesome. So to summarize, what did I just say? So I said we start with a W algebra, a certain level of GLR or G in general for, say, simply laced, or anything that is strongly generated here. Then out of this, you take the modes of the strong generators. So I'm using the same letter, but let's use, I don't know, MI, right? So these are the modes of the strong generators. I'm restricting to the positive modes here. And you realize those as differential operators. If you can show that they satisfy the degree and subalgebra conditions, then you have constructed an array structure. From the theory of array structure, you have a unique partition function, which is killed by the differential constraints, but this is nothing else than your highest weight vector. So in other words, the theory of array structure provides all the intermediate steps here. And what it does as well is realize the highest weight vector in a very, very explicit way as an exponential of a free energy where all these coefficients are constructed very, very explicitly by this topological recursion.
Sorry, I have a stupid question here. So maybe I didn't follow it completely. So where does the Whittaker vector fit in this story?
Oh, okay. You see this in 2 slides. So now we're doing highest weight vector. And then the question is, of course, how does the Whittaker fit here? Because it doesn't fit, but it will fit. Unfortunately, I'm taking more time than I expected. So I'll try to speed up a little bit, but it's coming. Yeah, Whittaker vector is coming.
Okay.
All right, so the question here is, can you actually do that? So can you construct a differential representations for these modes that take the form of an array structure? So here, what I meant here is that this is very explicit construction of the highest weight state. But the question is, how do you do that? How do you construct this differential representation? Well, it turned out it's actually not very difficult. So at least in the case of WK of GLR. So let me just outline the construction. If you know about W algebras, you probably know that this is actually a subalgebra of the Heisenberg algebra. And this is key. So the Heisenberg algebra here is basically the CFT of the R free bosons here. So you have your free bosons, which have, as usual, an expansion in terms of bosonic modes, of this form, and they satisfy the standard commutation relations for the free bosons. Now, everything is rescaled by h bar, so I'm not going to spend time talking about how h bar enters in the VOA construction. Basically, h bar is a parameter we have to introduce to index the conformal weights in the algebra of modes in the VOA, but that would take me too long to explain, so I'll avoid that. So there's an h bar here that would probably not be there when you do just a Heisenberg algebra. And then you have your standard commutation relation for your the modes of your free boson. And yeah, what you do is now you just realize, because these are the free bosons, then you can basically construct the generators of the W algebra as, because it's a subalgebra, you can construct those in terms of the modes of the free bosons. So if you look, for example, at the self-dual level, which is a lot easier. So this is the case where kappa is equal to 1, so epsilon 1 is equal to minus epsilon 2. So in this case, it's very easy, because these strong generators are just given by the field, the strong generators here, the field just given by elementary symmetric polynomials, and these J's. So again, this is very well known in the theory of, sorry, that should be I, of W algebras. So you just have a product of these bosonic fields. So from 1 to I of J of AI of Z, right? And then to extract the modes here, you just extract the corresponding powers of Z, and that gives you the expression for the modes here in terms of the modes of J, the bosonic fields. Now, if you want to do arbitrary level, then I'm not going to write down any formula because it's a lot more complicated. But there's something called the quantum Miura transform, which gives you a formulation of the strong generators in terms of the bosonic fields. So you can extract similar things, it's just much more complicated at arbitrary level, but you can do it. And then all you have to do to get an array structure is basically use a differential representation for your bosonic modes, which is a standard one. So you take the positive modes to be h bar times derivatives with these coordinates here that we're introducing. The negative modes will just be coordinates times m. And the zero mode will be given by a parameter, complex parameter QA minus alpha, where alpha here is just epsilon 1 plus epsilon 2. Self-dual level, alpha would vanish. Arbitrary level is not zero anymore. But if you do that, and you plug that in here for the modes, that gives you a representation for the modes of your strong generators as differential operators. And then you can prove that these satisfy the degree and the subalgebra condition, which is something we do. And then you end up in array structure. You end up with an array structure. And you can do that for arbitrary level using the quantum Miura transform. At self-dual level is very explicit. In general, it's more complicated, but it's still an array structure. And you can prove that it is. So you have constructed a representation of your W algebra as an array structure. All right, so that's cool. Now, I just want to mention that in this paper, previous paper, we do something much more general. So in this paper, we construct many, many more representations of modes as array structures by looking at larger subalgebra of modes, not just the positive modes, and also using representations that come from twisted representations of a Heisenberg algebra. You can also do that, and then you get all kinds of different array structures whose partition functions have various meaning in enumerative geometry. But that's for another story. Okay, but as was pointed out, this gives highest weight vectors, not Whittaker vectors. So I have only maybe 5 minutes left, and I still have a lot of things to talk about. So let me try to summarize what I want to say. So highest weight vectors, not Whittaker vectors. How can we get Whittaker vectors from array structures? So far, we can't. We always get highest weight vectors. But here's the nice observation. So this is a very simple observation in the theory of array structures, but it leads to some really interesting result. So if you start with an array structure, so you have a bunch of differential operators. So here I'm taking the case where it's infinite dimensional, as in the previous case. So let this be an array structure. Now suppose that there is something very special. Suppose that there is a subset of modes, whatever that is, and I'm going to define S prime prime as being by modes, I mean differential operators here. So this is a subset of the differential operators, and S prime prime is the differential operators minus that subset, such that if you commute any two differential operators, the answer is in the left ideal, but not generated by all S, only generated by those modes that are in S prime prime. So in other words, the operators or modes in S prime are not there here. If you have that, then that's pretty cool, because what that means is that you can define a new array structure. I'm going to call it H bar I by taking the old one and shifting all the modes in S prime. So you can shift them by any power of H bar, at least as long as it's more than one. So you have some constant here, whatever that is, could be anything. Alpha I can be any positive half integer or non-negative half integer, and then you have some constant here. So you can shift all the modes if this is an S prime, and if it's not an S prime, you don't shift it. And if you do that, you still get an array structure. So why is that so? Well, if you shift the modes, the commutation relations don't change, because the left-hand side, the constant, of course, commute with everything, and because these modes don't appear here, it doesn't change anything. So you still know that the subalgebra condition is satisfied, and if you have a power of H bar, that doesn't change the degree condition. So this is still an array structure. So you can apply Kontsevich-Subelman, and you get that the associated partition function, so you have a partition function associated to this array structure, which is killed by these operators. So in terms of the old one, the partition function now satisfy a relation like this. So this is if HI is in the subset that doesn't appear on the right-hand side, and it's 0 if HI and the rest. Now you see where I'm coming. That looks like a Whittaker vector, right? So this is how we construct Whittaker vectors. So what we have to show is that this condition is satisfied, so that some modes don't appear on the right-hand side of the commutation relations. And if you can show that, then you can we construct these shifted array structures, which will give rise to Whittaker vectors. All right, so I'm coming to our theorems, and that's pretty good. So I think I'll make it on time. Good, roughly speaking.
Just one, so how to see that the partition function would be the norm of a Whittaker vector?
So yeah, sorry, we shouldn't be confused. What I call a partition function here is not the partition function, the instanton partition function. So it's just an array structure Z. So I was using the instanton, I used some weird Z in the beginning, something like that. So it's just in the theory of array structures, Z is called the partition function, but it is not the instanton partition function. It will be identified with the Gayotto vector.
Okay, thanks.
All right, so now that leaves us to two theorems. So first, one thing that we proved, this is just from vertex operator algebra directly, is that for generic highest weight lambda and a Verma module of a principal W algebra, which is what we're looking at here, there always is a unique Whittaker vector in the Verma module such that this condition is satisfied. So it's killed by all positive modes except WR1. And we also proved that this condition that I just mentioned is satisfied. So if you commute any two of these positive modes, you are inside the left ideal, but not generated by all positive modes, generated by all positive modes except the one mode of the highest conformal weight generator. So that's exactly what we need for high array structures. And this is true. We can prove that from VOA point of view, that comes from the fact that it's strongly freely generated and all kinds of cool stuff in VOAs. Okay, but that's exactly what we need. So then we can construct an array structure. So if you use the representation for the positive modes of the strong generators in the H bar that I constructed before, so you just start by embedding inside the Heisenberg algebra, and then you restrict, you use the representation for the Heisenberg modes to construct your representation, then you can shift the WR1 mode because it doesn't appear on the right-hand side, and you still get an array structure, and the partition function, which is uniquely defined, is satisfy these constraints. So it's killed by all positive modes except one. And now you see, well, this is very cool, because what is this? Well, Z is nothing else than the Gayotto vector. So what we've constructed here is the Gauss vector. We've constructed very explicitly as the exponential of the free energy, where we can construct all coefficients recursively. But it's also kind of nice because we can also identify the energy scale in the theory. So this energy scale lambda that we had before is now related to this parameter t, but there's an h bar here, which is actually key for us. This power of h bar is very important. If it wasn't there, it wouldn't work because that would not be an area structure. So it is very important. So what it means is that what we are doing here, we're doing things for arbitrary level, so arbitrary omega background, but we're doing perturbative expansion in the energy level because it's basically proportional to h bar. So we are doing something perturbative in the energy level, which is kind of an interesting thing.
Vincent, can you just remind us what you mean by a partition function here of an area structure? A very general thing that you just said.
Yeah, the partition function of an area structure is basically the reason for the area structures to be constructed. So area structure was this collection of differential operators. The partition function was this thing that Kontsevich and Subelman proof is the unique solution to the differential constraints. So it's the thing that is killed by differential operators. But it has a very specific form. It's basically the exponential of f, which is a general power series, in x, and the coefficients satisfy topological recursion.
Yeah. Okay. So there's topological recursion among these coefficients, and you're doing it perturbatively in h bar.
Yeah. Everything here is perturbative in h bar. Yeah. Exactly. Yeah. So that's why we also have a perturbative expansion at this energy scale. Okay, so that's pretty cool. And then just a few remarks before I end with a few upshots. So I did only the GLR really case, explicitly here, the GLR case, but we can do the exact same construction we do in the paper for the D, for type D. So in that case, you still have strong generators, but they're still embedded inside the Heisenberg algebra, but the explicit expressions are more complicated. But you can prove that they are area structure and then that the partition function is the Whittaker vector. That is the Gauss vector for the corresponding gauge theories. For type B, then the Gauss vector is a Whittaker vector, but it's not a Whittaker vector for W algebra of B type, because the theorem of Braverman-Finkelberg Nakajima is only for simply laced the algebra, but it is expected from physics that the Gauss vector will be a Whittaker vector, but for a twisted module representation of A type. And this is something that we actually construct explicitly. We construct the area structure, but in this case, we cannot prove the subalgebra condition. So our construction works, but it's subject to the assumption that the subalgebra condition is satisfied. And it's the same thing for type C. In this case, it's a twisted module for W of type D. And again, our construction just works, but we have to assume the subalgebra condition. We can't prove it explicitly. Okay, so that's basically the general construction. We start with W algebra, construct a differential representation, and then we obtain a very explicit construction of the Gauss vector as the partition function of the area structure. Now, there's a lot of things we can do with that. So one thing that we do in the paper, so I won't talk about this here, I'll just say see paper, is because we have a very explicit recursion for the coefficient of this partition function, we can extract all kinds of nice or cool structural properties for the Gauss vector and its corresponding instanton partition function. So that's something we do. We obtain some results about this. I don't know how interesting they are for gauge theories, but it's something, as I said, one of the things is we can start using all the things that are known in the abstract structure of topological recursion and try to interpret it now in terms of gauge theories. So that's a starting step in that direction. But another thing that we do, so I won't have time to talk about this, but if you know about spectral curve topological recursion, so as I said, Kontsevich-Subelman's construction was an abstract formulation or algebraic formulation of the Chekhov and Untitled topological recursion, which was based on the geometry of a spectral curve. So just to highlight a little bit what we do, so in our paper, we do reconstruct the spectral curve topological recursion in the case of GLR and also type D, so SO of 2R. In the self-dual level, we get everything very explicitly. And in fact, the spectral curve, so the starting point here is a very, very simple spectral curve. It's basically just a product of linear factor. So something like that. So if you know about topological recursion, usually the spectral curve are higher degree polynomials, but if you think of the X projection on the X-axis, this would be a ramified covering. So here, this is unramified. So this is different from the standard in our topological recursion. In fact, it's simpler. It's not the Seiberg-Witten curve here. In fact, it's the lambda. You can relate it to the lambda going to 0 limit of the Seiberg-Witten curve, which is related to the fact that our lambda is proportional to h bar. And most importantly, it's very simple. This is probably the simplest type of curve you could look at. And it turns out to encode all the information of the Gauss vectors. It's kind of magical. And at arbitrary level, we can also do everything. And now this is interesting for those who know about topological recursion, because now this gives rise to a new formulation of a non-commutative generalization of topological recursion. And here we don't have a spectral curve, but we have a D module. So the geometry is all related to the solution of the differential operator, or the D module here, which looks like this. So I'm just going to write it down without commenting further. But if you're interested, you can look at the paper. It's very complicated to do it for arbitrary level, but we do manage to do it in the GLI case, and we get explicit expressions. So it's kind of cool if you're interested in these things. But yeah, so that's one thing that we get. And in the case of SO2R, we also do it. We get a topological recursion on a spectral curve that pretty much looks like this, but it's a double cover of this. And then this is a new topological recursion, which we call B type, and D type, sorry, in the case no, sorry, we just do it for the self-dual level in this case. But yeah, we get this new topological recursion. Sorry, that's not the case we do. That's the B type. Sorry, confused here. Anyway, we write it down explicitly in the B type at self-dual level, and then we get a nice topological recursion as well. So if you're interested, you can look at the paper for this. All right, so I'm going to conclude now because I'm already an hour in. So the general story here is that we start with W algebras. We construct differential representation as differential operators acting on the space of formal series for the modes of the strong generator, the positive modes of the strong generator. We prove that these take the form of an array structure, so we can use everything that is known about topological recursion. In particular, we know for free that there exists a unique solution to these constraints called the partition function, which is nothing else than the Gauss vector if we look at these shifted array structures. So it's pretty cool. So we have for free the construction and the existence uniqueness of this Gauss vector. And a few things we will discuss in future work is first is what is the relation with Seiberg-Witten curve? So this is something that has been studied before. So, you can also use the Seiberg-Witten curve to study these theories. So a Seiberg-Witten curve is related to our curve, but it's not quite the same. It looks, at least it's related to this curve here where you have a right-hand side, which makes it a lot more complicated. So we're looking at the case where lambda goes to 0, but the Seiberg-Witten curve is a lot more complicated. You can do topological recursion on these curves. This should be related to the instanton partition function by all work. But what we're doing is a lot simpler than that, and we get the Gauss vector directly instead of the instanton partition function, and it's a lot simpler. But the question is, how is it related? So this is something we're working on right now. And the last comment I want to say is that we can generalize our construction easily, at least from the point of view of array structures. So what we have to do, we can look at smaller subset of modes. So instead of looking at all positive modes, we could look at smaller subsets of modes as long as they satisfy this subalgebra condition. We can also shift more than just one modes as long as they don't appear on the right-hand side. So if we can prove that they don't appear on the right-hand side of these commutation relations, we can shift them to construct more array structures. So that gives rise to many more kind of Whittaker type vectors. So things that are killed by a subset of positive modes, but such that some modes act as constants. So we could in principle construct way more things like this. And the question is, what are those? And well, it turns out that in physics, these seem to appear in Argyres-Douglas theories, which is something that we will study now. So it'd be great because these are much less well understood than the Gauss vectors. So potentially we can prove existence uniqueness of all these things using the theory of array structure. So that'd be really cool, but this is work in progress or work that just started. So yeah, I guess I'm going to stop here because I'm already past my 50 plus 10 minutes. So thank you very much.
Thanks, Vincent. It was really a very enjoyable talk. Although I must confess it was a little challenging sometimes, but because of my lack of mathematical background. But I really enjoyed. And so let's have some questions now.
There was in the early 90s, Kontsevich and Witten, and then also there was a Liouville theory coupled, matter coupled to Liouville theory. So there are all these W constraints. Do they also fit into this story in any manner?
So what are these W constraints? What are the theories?
So these were, I mean, there are many avatars of it. So one of them would be topological minimal models coupled to topological gravity, or Liouville theory coupled to minimal matter and stuff like that.
Right. So this is related to W constraints.
Partition functions
models.
to satisfy these kind of Virasoro and W constraints. And
right. So these are related to W constraints satisfied. I mean, you can construct corresponding matrix models, right? I think, and then you have W constraints.
Yes. There's also a matrix model construction of that.
Yeah. So I mean, this also. I guess in this case.
Does it go through the
W
AGT
constraints
again?
in general? Sorry.
Does it again connect up through AGT in some sense? The 2D version, or it's a different story altogether, because all these structures, similar structures seem to be there. But I don't.
Yeah, so there's a few things I can say. I don't know if it connects to AGT. What I can say is that, I mean, the origin of the topological recursion, I didn't even mention that in this talk, but the origin of the topological recursion is in matrix models. So it's to construct the correlation functions in your matrix model, right? So the expectation values of the traces or the matrices. Yes. Now, these are not, and then you can reformulate this topological recursion as an array structure. These are not the same as the Virasoro constraints satisfied by the partition function of the matrix models or the W constraints in these general case, but it is related. You can relate the two. It's non-trivial relation, however, but you can relate the two. So I think the W constraints you're talking about probably don't take the form of array structures. They're kind of similar to the Virasoro constraints you would get for the standard matrix models. But I don't know if it's related to AGT. Gaetan, am I saying things that make sense in your opinion?
Yes. I think sometimes the gauge theory partition function can be written as a matrix models. I don't know how general it is, but there's something like this. And so you could think that you have in general the large world of W constraints. And in some instances, this is W constraint of matrix model or topological gravity. In some other instances, it is related to Gayotto vectors of gauge series. And topological recursion somehow applies to all of that world. Not necessarily in an obvious way. As Vincent mentioned, there's some relation, but one has to work, and this work has been done for matrix model, for example, to relate that to array structure and then topological recursion. But yeah, this is the same world, and topological recursion is exactly supposed to be able to touch the two.
Yeah. In that context, there were extra times which are related to the deformations. So is there some extra structure like that here? I mean,
so the extra times in that case, they are, so that's the thing. So the Virasoro constraints in your matrix models would be derivatives with respect to these times, right?
Yes. Yes.
So I mean, here the derivatives are in the coordinates x, and, yes. And these coordinates x is here are I guess it's different. They're coming from the representation of your Heisenberg modes. So I mean the x's that are introduced here play the time would be the times in these W constraints and matrix model, the Virasoro constraints and these things. So
correct. Actually, you're right. Yes, because the degrees work out.
So yeah, it's kind of, I mean, I guess that's how, as Gaetan said, it's not so, yeah, it's not so easy to relate. I mean, you can relate the constraints on the partition function of the matrix models, or those type of constraints you're talking about, to the staying in matrix models, to the topological recursion satisfied by the correlators. But on one hand, you have the times, and the other hand, you have the x's, which are the generating parameters for the expectation values of traces that you use to construct these correlators. So again, these are not the same variables, but you can go from one to the other by doing some work in matrix models, but it's not completely trivial.
Thank you.
I'm not explaining. I'm not
No,
helping.
it's okay. I mean, for me, it's like now more than how many years now? 30 years ago. So I haven't looked at it after that.
I think some of
Memory is
these
fading.
matrix models are there in open intersection theory, right? Like these what Suresh was talking about. Like I think some of them have geometric interpretation as counting open intersection numbers. So maybe that's related to things. Like these extra times, the Kontsevich-Penner matrix model has just even times, but when you add these extra times also have odd times, and they are related to these open intersection matrix models. I don't know if that's exactly what Suresh was asking about, but that sounds familiar.
Yeah, I mean these. Yeah, I don't know. Any more questions, comments?
Yeah, actually, I have another very nice question. Maybe I should also address it to Gaten and you both. So you had this in topological recursion, I think this genus, higher genus is appearing. So from the 4D 2D correspondence, how to understand why the higher genus should also appear? Because in the usual Galacto story, I think the genus is fixed in the AGP story. So I'm just
so you're talking about the genus of the 2D, the target of your 2D
partition
CFT.
function. Yeah, the partition functions had genus expansion.
Right. So this is not the genus of. I mean, it's the same thing when you do. I mean, it's a different context, but I mean, so you here. I mean, the CFT, if you want, is fixed. The genus of the target curve, where the CFT live, is not the G that we're doing an expansion on, right? So this G that we're doing an expansion on is the parameter, the power of H bar, if you want. I mean, if you think of it. I mean, the G we're doing an expansion on is kind of the world sheet genus, if you want, and not the target space genus. I don't know if I'm making sense, but you know, in the sense that we're doing an H bar expansion, but the CFT itself is kind of fixed, if you want, or the theory that you start with is fixed. No?
Okay, yeah, I will. I get some idea. Yeah, thanks. Yeah, I was just trying to understand some kind of physics interpretation of this recursion relation, in some sense that it's a. I mean, it can be reinterpreted in some physical language, this recursion formula.
I mean, you can. So in a sense, I mean, we're writing the Gayotto vector as exponential of this expansion in H bar. That's what this G index is. And from there, you can also write down an expansion for the instanton partition function. And then you can interpret these coefficients in terms of the instanton counting. And you're starting.
Okay, I see.
In fact, we do that in the paper. In the structural properties, when I said C paper, that's exactly what we do. I mean, it's a bit subtle here because of the fact that lambda depends on H bar. So in fact, we have to kind of resum or re-expand. So the expansion that we have in H bar should be re-expanded in a sense, because we also want to use this power of H bar. But if you do that, then you can write down the corresponding expansion for the partition function, and then you could interpret the result in terms of instanton counting.
So this is similar to the kind of localization results people use for counting, for computing this recursive partition function directly. I see.
Yeah, I don't know how that relates to this, but yeah.
Okay, thanks. Yeah.
So maybe I can add what when Vincent said. So indeed, it's not in that paper, because here we're doing this perturbative thing in lambda. But somewhere in the next paper, there will be finite lambda. And then indeed, you can somehow reprove the result of localization. using topological recursion techniques.
I see. Because I'm more familiar with the later one. Okay.
Yes, because what this localization means that your Gayotto vector or your instanton partition function is a sum over partitions, so Young diagrams with certain weights. And in that particular case, this particular geometry that we're looking at, this is essentially, if you do localization, you find a generating series of Hurwitz numbers. So counting branch covers that physically dates back to Witten, and then various people also noticed that. And knowing topological recursion, there's also connections to Hurwitz theory. So it's a kind, you close the circle. You start with a supersymmetric gauge theory. You can either do localization, and so you recognize Hurwitz numbers, or you can say, well, I first look at the W constraints. I solve them by topological recursion, and I prove it's also generating series of Hurwitz numbers. So it's different ways of approaching the thing.
Interesting. So indeed, it has some kind of a wall sheet represent as interpretation, like Vincent was saying. And, I see.
Yes, and so some of that's the side that says on the 4+2 if you want, but also this. So the worldsheet interpretation, it's also because you can think of this topological recursion as a topological strings B model. You would have a string theory that's geometrically engineered from the gauge theory, using some geometric transitions. And some other topological recursion is a shadow of what's happening on the topological string theory.
I see.
So yeah, it's a B model, and the spectral curve is the underlying complex variety, which is just a curve on which you do period computations to get the B model, and that's essentially what topological recursion is.
Yeah. So I mean, I guess in the context of gauge theories, I don't know how clear that is, but at least in what Gaetan was saying is in the context of topological string theory. I mean, there's this old work remodeling the B model and the many papers that followed, which was exactly that statement. If you start with on the A model side, you start with topological string theory, where your target space is a toric threefold. Then on the mirror side, which would be the B model, then you can prove that in fact the B model mirrors just topological recursion on the mirror curve, which turns out to be the spectral curve of this topological recursion. So that's kind of the story from 14 years ago or something, 13 years ago. Well, that was only proved, I don't know, 7 years ago, whatever. But this has been studied for many years. So that's in the context of mirror symmetry, but then you can extrapolate. And for Hurwitz numbers as well, you can think of topological recursion as being kind of a B model of Hurwitz numbers, of all these counting problems. So these interpretation I was saying of these FGNs as counting things, it's kind of an A model type interpretation, and the B model is this topological recursion construction. That's the general kind of spirit. And now we're doing things in the gauge theory context. I guess I'm not as, it's not as clear to me in my mind that this same interpretation holds here from what we're doing, but Gaetan might be right, that you can think of it as well as a B model of these things, but yeah.
I would say just as an intuition, this sounds right.
Right. And in that case, that's really a worldsheet. What I was saying before, so the spectral curve here is the target space. So you use kind of the mirror manifold to these toric threefold. So for example, the genus of the spectral curve is fixed and doesn't change. This G that we're expanding on would be the genus of the worldsheets, the strings you're mapping to your target space in your sigma model, in your topological string theory. So that's what I had in mind when I said this kind of a worldsheet type expansion.
Yeah, thanks. Yeah, okay. Hopefully such a thing really exists. Okay, thank you. Yeah. Okay, any further question or comments? Okay, if not, then let us thank Vincent again for this very enjoyable talk, and and hope that Vincent and both Gaetan can visit us at some point here in Chennai. And,
Hopefully one day when we can travel.
Yeah.
when we can travel.
Well, thank you very much
Okay.
for the invitation. That
you.
was very enjoyable. And talk to you soon.
Okay, see you soon. Have a nice rest of the week, rest of the day. Bye.
All right. Bye.